All right. So we have Pooja looking at Maar deposits. Is this Trans-Mexican belt? Okay. Yeah. So that strip that goes across the middle of Mexico at this strange angle.
Hi, very good afternoon to everybody. I hope you guys are not feeling sleepy yet. Okay, and not in a rush to have some snacks and coffee, I guess. Uh, I'll just discuss about my preliminary investigations which I carried out for my postdoctoral work right now in UNAM, and it has been just 9 months that I have been there. So and the area, especially this Alberca de Guadalupe, is never been studied before. So it's like basically I don't have any reference data, or I don't have anything to start with. It's like maybe I will be laying a foundation for it, kind of like that. So to begin with, let me tell you what this Alberca de Guadalupe means. Alberca in Spanish means swimming pool, as you can see there. And the Guadalupe is Holy Virgin. As you know, Spanish people are pretty religious. And if they see something like really beautiful, they would like to call it holy, right? So basically what I'll be talking is I'll give a brief introduction about the Trans-Mexican Volcanic Belt. Then I'll be reducing the area, to the Michoacan-Guanajuato volcanic field. Michoacan and Guanajuato are basically two states which cover this volcanic field. And this volcanic field is monogenetic. I hope people here have some idea about what monogenetic is. Monogenetic is like having one episode of eruption, one genesis, one eruption. We don't have big volcanoes, but we do have numerous small volume volcanoes which forms the monogenetic volcanic field. Then I'll be again reducing the study area to Sakapu. Sakapu forms the central part of the monogenetic volcanic field, which I'll show you in the map. Then I'll discuss the phreatomagmatic vents which are which are encountered in this area, which is quite strange considering the tectonic and the climatic conditions in this area, to find some phreatomagmatic vent over there. Then I'll discuss about some preliminary investigations which I have done so far. It's really, really basic. Actually, I find it embarrassing after seeing so much plots and so much argon data and all that. But it will be done in near future. And then I will try to decipher a general research direction through that. Whatever preliminary investigation I have carried out, I have a rough idea about what must have happened back then. Although right now I don't have really robust data, but it's still in process. The work is still in process. So to begin with, as you can see, Trans-Mexican Volcanic Belt. We are in the state of Mexico, and it's pretty interesting. There is this Rivera Plate and Cocos Plate, which are subducting in the Northern American Plate at different rates. And you can see that there are several volcanoes which are shown in the red triangle over here. And this part is like Trans-Mexican Volcanic Belt. And the angle is, basically because of the different rate of subduction. And also the unique part of this subduction zone is like, initially you will have a general subduction slope, but then later the subduction becomes quite flat in this region, and then again it becomes steep. So it's quite complex environment, if you see. And when I arrived to Mexico, I thought that, I can work on bunch of really active volcanoes from wherever I want and do some. Basically, I wanted to work physical volcanology, how it is used and all. So I can pick up my volcano, but it was not the case, as I realized that there are wolf packs over here who have their own territory. So it was like I was working with Klaus. So Klaus said that he has a project which is like on Michoacan, Guanajuato. And also it's like the Guanajuato is in the upper, the Guanajuato state form the upper part, the northern part of this field. And Michoacan is the southern, over here, this part. And within this Michoacan Guanajuato volcanic field, I got a really, really small area, which is this Sakapu, where I can have my investigations on the physical volcanology. Yeah, so it didn't work. Being Moreno, it still didn't work. So, okay, so the fun part about Michoacan Guanajuato volcanic field, it's, as you can see, there are these gray dots. So it's filled with thousands of scoria cones, cinder cones. Thousands, more than thousands, and still the number is going on. People are adding and like finding out more cones. And of course, it is also famous for the presence of Paricutin, the historic eruption of like 1943. And another historic eruption was like Horullo, which is in 1759. So my study doesn't have to do anything with this, although they sound really interesting, but I didn't get the opportunity. So the next thing is like I will like to discuss about the Sakapu area, the little piece of meat which was given to me to chew on. Now, yeah, if you see, as I was saying, that there are thousands of scoria cones in this field. So there are shield volcanoes, there are stratovolcanoes, and then there are these cinder cones. Also, there are domes. So you can see as it's getting crowded. I come from Mumbai. It makes me feel like really crowded. And then I was like, okay. And then I was like, what's wrong with these volcanoes? I mean, they just wanted to erupt wherever they want to. I mean, even if we try to plot an alignment or try to see a trend, it's everywhere. It's like radiating. There is no, you cannot actually, say, oh, it's erupting along this fault, because the area is highly faulted. And along these faults are like, there are two trends of faults. One is like basically east-northeast and west-southwest. And then there is east-west. Well, there are a few volcanoes around east-west. And then there is another northwest and southeast. So in this manner, how can you really align these scoria cones? So it's like, it's just crazy in there. So this is how the Michoacan Guanajuato volcanic field looks like, which got me pretty excited. Now, confining my study area, as you can see, this is a Sakapu basin. I am referring it to a basin because it was a lake. Before 19th century, it was a lake. But in the 19th century, in order to gain agricultural land, this lake was like artificially drained out. So now if you go there in this place, it's just a flat pasture land, which is used for cultivation. And for my postdoc, I am looking at, let me first describe about the geology, about the volcanology. And you can see here the red color are Holocene, which is very few. Then the yellow ones are the late Pleistocene. And then you have the mid-Pleistocene, early Ignimbrite, a few Ignimbrites over here. And the oldest is the Pliocene volcanics, which I found in my study area over here. And as you can see, there are so many scoria cones. But in comparison to the number of scoria cones, I just found 3 phreatomagmatic vents. One is over here, Alberca de Guadalupe, on which I'll be discussing today. And next is the El Caracol. And the third one is the Alberca de los Espinos. Espinos is spike, thorns, and caracol is snail, because it has a morphology of a snail. So yeah. Why are these Maars located here? probably because of the lake. Well, yes, but more than that, what are the local? I mean, it's not just a matter of Sakapu Basin or Sakapu Lake, because there is a lake on the eastern side which is Kutseo. There is another lake which is Patsquaro, which is below south over here. But you don't find any Mars or any phreatomagmatic vents over there. Why only near this area? So it's not the matter of lake, but it's, I think, the local conditions or the local geology which is influencing the formation of phreatomagmatic vents over there. And how can I inference about this? So to begin with, I started making some early investigations on the deposits of the Alberca de Guadalupe. So to begin with, as I want to give you a brief review on the types of the monogenetic volcanoes, how they manifest themselves. Based on the water and magma ratio, like phreatomagmatic eruptions and all, you can have 4 different forms of phreatomagmatic vents, and Alberca de Guadalupe belongs to this category. As you can see, my volcano doesn't grow like this. It grows like this. So I have very few tephra deposits to study. And these tephra deposits, they're pretty interesting because they give me an insight of what is lying beneath the subsurface. And as you can see in the previous map, there were so many volcanics in Michoacan Guanajuato field. Over here you can see there were like so many volcanics of different age, which is lying one above the other. So it becomes very difficult to find out what exactly is beneath. I mean, the Pliocene is not present everywhere. So it can be like the late Pleistocene can be laid by directly early Pleistocene, and there is an absence of mid-Pleistocene. I cannot just put mid-Pleistocene just because of the geological stratigraphic scale, time scale. So it's pretty interesting because it gives me the stratigraphy pertaining to this area only. Maybe if I do more studies over here, it might give me another stratigraphy, and here as well. So it's really different. Even in the scale of like 5 kilometers, the volcanology is really different. So to begin with Alberca de Guadalupe, as you can see, it's an enlarged image. The same color pattern has been used for the age. Here you can see this is the crater, the Alberca de Guadalupe crater. And here are the early Pleistocene volcanics. Now another important factor that I would like you to keep in mind that is presence of this small scoria cone, which is called as Seropelon, about which I would like to discuss. And I would like to tell you what is the connection between these two. So before I arrived to Mexico, a lot of investigation on the age parameters were done with the help of radiocarbon dating, argon-argon dating. And in this area, we found some paleosol samples, which was dated by Dr. Klaus Siebe and his team. And the age came out to be like 20 to 23,000 years. And as you can see, this bluish thing is a lava flow. It's a flat lava flow. And if you go to this place, you will not realize that there is a hole, literally a hole inside the topography. I mean, if I see, I'll show you in the next picture. If I see, it just looks like a flat plane. And this lava flow, with the help of geochemistry, I tried to, initial geochemistry or like preliminary geochemical data, it helps me differentiate the lava flow. It helps me determine that the lava flow comes from Cerro Pelon and not from Cerro Picacho, as both of them have like early Pleistocene age. But the geochemistry is different. And as you can see, that this region is affected by so many faults, which are dipping in like domino style. And most of them are dipping towards northwest, towards the lake. This is actually the Sakapu Paleo Lake. As you can see, it terminates over here and not here. So there should be some way of presence of water, which led to the formation of this phreatomagmatic vent. Over here, again, I would like to explain that this yellow color marks the drainage basin area. And with the help of the ArcGIS software, I try to make some drainage pattern. Also, if I see the morphological parameters in comparison to the volcanoes which are discussed here, it's a itsy bitsy volcano, really tiny. Well, that's what I got. So yeah, and the depth is like 149.3 meters. Why so different? Why do we find this volcano here? So the field observation, as I said, this is Cerro Picacho Kendo, which was on this side. This is that scoria cone, Cerro Pelon, and here below you have the lava flows from the scoria cone, and you see that the topography is pretty flat. I mean, and here is a road. So for a couple of distance, you cannot even recognize that there is a hole inside this of 140 meters. So that's pretty interesting. So once you go there, you immediately see that there is a steep hole. So yeah, if you go through the road over here and you come to the viewpoint, which is behind this, you will have this kind of view. Now you see that there is a beautiful lake. You can approach the lake, you can swim. And also you can see that these lava flows of Cerro Pelon, and this whole crater is actually faulted. And this fault, the fault actually gives different, I mean, if you can see the amount of search deposits or the Tephra deposits over here is different than the amount of deposits over here, which actually says that the fault was active during the formation of this crater. And also there are local debris flows because of the presence of the gravity-driven environment. So the deposits, there was just like one small outcrop, and it was actually the picture which I showed you. It's a viewpoint, and then towards the left you have a small pathway to go towards the lake. So along that pathway you find this kind of deposits, which is like not so much, but it gives fair idea about what kind of an environment it is. As you can see that there are many fine ash surge deposits. As you can see that there is no nice mantle bedding or something like that. The deposits are pretty distorted, cross bedding, and there are like well stratifications of like alternate stratifications of coarse, then fine, medium, lapilli size deposits, and here is a pen for scale. And within these deposits, you can see that there are ballistic bombs. Now this is a quite smaller bomb, but in the next slides I will show you the that there were huge ballistics which were thrown out, which gives me an idea about what kind of an environment it was back then. Also the deposits, here is a lens for the scale. Also the deposits are faulted by the listric faults along the inner wall of the crater. This is because of the gravity pull, and nothing to do with the regional fault which I explained you before. Also we can find several accretionary lapillis in the way fine surges or fine deposits, which helps me interpret that the environment was pretty wet. Now the size of ballistics or the xenoliths, as you can see, it was pretty huge. And here you can see that there are fine ash deposits, then there is coarse, then there is again fine, and so on. This is at the rim of the crater, and I could find that there were like pretty unusual accidental lithics. I mean, it looks like an ignimbrite in hand specimen if you see, and this was pretty different than the ignimbrites which are found close by near this volcano. So I decided to do like componentary analysis, which is in process right now, but I'll discuss about this a little bit later. And a little bit on Ceropelon, the scoria cone, whose lava flow is lying underneath the deposits, the surge deposits of the Maar. As you can see, it is not a big scoria cone, but it has effusive kind of an eruption. This is the cross section of the scoria cone. The area is under quarry, so we couldn't get really like good area to do some stratigraphic sampling or something like that. But the juvenile bombs were collected from this area for the geochemistry. So if I tried to determine a rough stratigraphy for the deposits which I find on the way going down towards the lake, the initial part is like it's having a lot of impact sacs, then alternate coarse lapilli, fine lapilli deposits with some accretionary lapilli, and then there was a break because there was some house built over there, so they just excavated the deposit and made a nice lane towards their house. So I did not find the deposits over there. And then later on there is continuation of the deposits, where you can see that the deposits are getting the coarse lapilli deposits are more as I go more towards the crater, towards inside the crater. So, and these deposits are like mainly affected by the listric faults, whereas I did not find any listric faults over here. And surprisingly, I found that there was a paleosol, and below the paleosol I can find another ignimbrite ash, but we don't know where this ignimbrite come from. It's not from the area which is close by. It's not the ignimbrite xenolith, which looks similar to the xenolith which I found on the crater of the rim. So it's pretty complex. So I did granulometry analysis on few of the samples over here, and I could see that it's poorly sorted, and the lithics concentration is of course more, and the lithics are basically I could find three types of lithics. One was like gray lithics, which is like more or less it looks like the xenoliths which are coming out from the fragmentation of the Ceropelon lava flow, which is the underlying lava flow. And then next is the ignimbrite, which I discussed, which I showed you the picture, but in small fractions too, I can find the ignimbrite lithics. And then I could find some dark gray basaltic andesite lithics. And the overall concentration of this is like 54 to 88%, which is quite okay for the Maar deposits. Like Maar deposits are actually classified with high concentration of lithics, so it's okay. Then the juveniles were in the form of cauliflower bombs. Some of them were fragmented, some of them were like intact, and the overall percentage is like 46 to 12%. Then, yeah, I took an intact juvenile bomb from one of the deposits and made a petrographic slide. As you can see that there are vesicles in here, nice plagioclase crystals, but there are a few xenoliths or accidental lithics which were caught up during the eruption, fragmentation. And then there was this, again, the fine ash in which the accretionary lapilli was embedded. I took, it was fairly indurated, so we can make a thin section out of it. So the fine ash is mostly contains glass. Then there are a few, again, lithics. And yeah, this is the accretionary lapilli. I would like to emphasize that I am at the preliminary investigation, so I have to make more detailed studies on this, like what kind of glass and what kind of lithics are they, basaltic. I mean, generally all the lavas in Michoacan or in my study areas, andesitic or basaltic andesitic. But I really need some good trace element data to distinguish between like from where exactly it is coming. I mean, just basaltic andesite is not enough for me. So I still have to do all these studies. Then these are this is the distal ash, like distal as in the distal ash deposit is found like just 1 kilometer away from the cone, from the crater. So maybe for St. Helens people, it won't be distal. I mean, for them, it's like, really? Your volcano is so tiny? Okay. But for me, yeah, it's a distal ash, and there was like less than a meter of a deposit, which was like fairly indurated, basically consisting of fine ash. And it was indurated, so I tried to make a thin section of it, and I can see that there are different types of lithics. As you can see, this one, it looks different. Then here, it again looks different. So there is different types of lithic, and I want to know that where are they coming from? Are they early Pleistocene lithic? Are they Miocene lithic? Within the Miocene, they are like coming from which volcano exactly nearby? Which shield? This is another slide of a xenolith, the gray xenolith, the huge one, besides which I was posing like really tough. So yeah, this is the thin section of that xenolith, which looks pretty much like an andesitic rock. And this is the thin section of the lava block, which was collected from Seropelon, which is the scoria cone towards the south of the crater. And you can see that it's mostly like consisting of glass. It's like less amount of phenocryst in them. And this is another xenolith which was encountered on the rim of the crater. So again, it looks andesitic, but I really need to know that where it is coming from. Then the ignimbrite, which I showed in the last picture, this is a thin section of that. I can see that there is good devitrification structures like spherulites in it, and I have a probable estimation that where can it come from, because there are this kind of ignimbrites found in Morelia. Morelia is like 100 kilometers towards the east of my study area, and these are huge ignimbrites which are actually coming out from a caldera eruption. So couple of months back, I went there. I collected some ignimbrite samples from Morelia, and I have sent them for processing, for making thin sections, for doing geochemistry, and possibly if I can date them. But again, I said that area belongs to some another wolf pack. So I had to talk to the leader of that wolf pack, and he said that he turned out to be pretty friendly. So he gave me the age of that Morelia ignimbrite, and he said that it could be an ignimbrite which is like 16 million years ago. So like it's pretty interesting. The stratigraphy in my study area would be then like I have the late Pleistocenes, which is like 20 to 23,000 years ago. Then I have the early Pleistocene Seropelon volcano, and then maybe I have the ignimbrites, which is like 16 million years ago. So it's pretty interesting, and maybe I can correlate the ignimbrite from the 100-kilometer area, and possibly can put a new foundation to make a new project or something like that to investigate where that ignimbrite is coming from and why it has traveled so far, something like that. So yeah, I collected some samples from the juveniles from the Maar, and also there were some samples in the records from my study area. Here you can see I'm following the same color pattern. The red ones are the Holocenes, the green ones are the blue ones are the early Pleistocenes, and the yellow ones are the late Pleistocenes. So my juveniles are actually triangles, yellow triangles, which are falling in the basaltic andesite region. And yeah, as you can see that, yeah, the preliminary K2O versus SiO2, whether my andesite is high silica, low silica, low K, or dacitic. So yeah, basically the yellow triangles is the juvenile bombs from the Maar crater. The blue or the bluish green triangles are the lava basement from the Guadalupe crater, from the crater wall. And this square are actually the lava blocks from the scoria cone of Seropelon. So as I told you, that how can I be sure that the basement which is below the crater was from Seropelon? So with the help of this with the help of these samples, I can say that the lava was from Cerro Pelon. So yeah, this are typical calc-alkaline conditions. And with the help of the primitive mantle normalized pattern, I could differentiate that the juveniles of Alberca de Guadalupe, they have a pretty different pattern from that of the early Pleistocene Cerro Pelon volcanics, from that of the early Pleistocene Cerro Picacho Kendo, which is towards the northwest side. So every volcano has its own chemical fingerprint, which I can, so this kind of data will actually help me interpret like which volcano is below which or which kind of rock I find. So I still got more things to do, but these are the preliminary investigations. Now again, paleo environment, another wolf pack area zone. But I tried to enter this, and this was in another department, and turned out to be there was a professor who is Indian, so he agreed to help me. So yeah, I went there, and he is not working in the area of Sakapu, but there was another team who is working over there. They have taken some core from the basin area. They have 3 cores, and the cores are in process. But the preliminary data, or the amount of work so far, whatever is done on the cores, it shows that Sakapu Basin was a deep water lake, somewhere around 28,000 years ago. And then later on, it started drying. And then later on again, it started deepening. But I don't know why. I still have to figure out why. And then there are, at the end of the 19th century, like in the early 19th century, the Sakapu Basin was drained artificially. So I have a rough idea about the paleo environment condition. But as you see, that my event is like somewhere around 20 to 23,000 years. But the lake was deep before 28,000 years ago. So for me, if you see, if this is the Sakapu Basin, my volcano is over here. And if it was deep, if it was filled with water, even if it was filled with water, there was no possibility for the water to seep into this area, because the basin is like dipping towards on this side because of the faults. It cannot go up. So I need to find a source of water for the formation of this crater. And the source of water was the springs, shallow water springs. So I investigated the area hydrologically, and I found that there were several shallow water springs which still persist today. I took the water, I did chemical analysis on them, and they turned out to be normal meteoric water. There is nothing hot spring or geothermal activity going on there. So for me, if you see, I tried to also do paleo topography with the help of ArcGIS, and it showed that the drainage pattern or the drainage basin doesn't change much. So which gives me an idea that, okay, the hydrological condition was pretty much similar like it is today. So this could be the reason, because these springs are like with very high discharge rate. So there is enough water for the eruption event for the formation of a Maar vent. Now, in the case of Guadalupe, there was favorable hydrological condition. There was nice tectonic fault through which the magma could ascend easily, but the magma supply was limited. That's why there is a Maar. If there was enough magma supply and the water supply was less, there would have been a scoria cone. And this kind of scoria cone, like a Maar turning into a scoria cone, I find in another 2 phreatomagmatic vents in Sakapu. So I would like to really study what was the local hydrological condition over there. So it turned out to be like the classic Lorentz or Valentine's Maar formation theory. Like if you have a magma rising onto the surface, you have a shallow water table condition, the magma interacts with the water, there is stream explosions, and my volcano doesn't grow this way because the water level keeps on dropping. So it will interact at more shallow depths, at more deeper depths, and then my volcano will increase towards inside the substrate like this. And then when the magma supply is stopped, the whole thing is like filled with water again here. That's why I find a beautiful Alberca in my crater. So in order to summarize the whole thing, the fault, which actually helps the magma to extend easily, and if I assume that the hydrological conditions were like today, so there were like shallow aquifer conditions which promoted the deepening of the crater and generally like excavating the substrate. Later on, the explosion were mostly stream driven because I could see many fine ash and accretionary lapilis, which was further on like mainly surge dominated and ferrotomagmatic event. And later on, yeah, that's it. So this is how I'm like